Hi, we're Group 18 in Staff 512, and our project analyzes the impact of different factors on insurance costs. So some background for our project. In the United States, there's been a problem of rising insurance costs. Many Americans struggle to even afford health care. So we found this quote that says about 4 in 10 US adults say they have delayed or gone without medical care in the last year due to cost. These high insurance prices may be due to lifestyle choices, drug prices, or other factors. And the cost of medical care can differ among groups of people. For instance, half of women say they have to put off or postpone getting health care they need because of cost, compared to about 1/3 of men. So in our analysis, we wanted to find out if certain categories or habits among people could correlate to individual medical costs billed by insurance companies. So our general research question was, are there certain factors or behaviors among individuals that can be associated with high health insurance costs? And our data set was, we found on Kaggle, which detailed insurance costs associated with a bunch of other variables, such as BMI and age. And some of our variables here, so we had a total of 7 variables, and then one was our insurance charges. So the first variable we had was an ID for each of the responses. The second was sex. Third was BMI. Fourth was the number of children. Number 5 was a categorical variable based off if you smoke or not. And 6, 7, 8 were all categorical variables for specific regions. So our hypotheses, we had 3 questions. Number 1, does living in the Northeast have the same impact on living in the Northwest on individual insurance charges? Number 2, does smoking have an effect on insurance costs? And number 3, will the BMI have the same impact on insurance charges if the person is a smoker or not?
So now as we dive into individual questions and analysis, we can first begin on question 1, which is, does living in the Northeast have the same impact on living in the Northwest on individual insurance charges? Kind of a way to essentially look at, does living in a certain region have or lead to higher costs than living in another region? To take a look at this question, we wanted to look at the variables of charges or insurance charges as the Y, ID as a unique identifier for each individual, regions as the 4 different regions, respectively, Northeast, Northwest, Southeast, and Southwest, and then the impact of ID on regions, or the interaction term between the two. To begin analyzing this, we essentially created just a simple model or an MLR model of all of these variables together mentioned in the previous slide, and this was our summary output. What we can kind of gauge from the summary output is that we had an extremely low R-squared value. Now, typically, we would associate this as being a poor model, and certainly in the future, to kind of mitigate this, we would look at adding additional variables to lower that or to increase R-squared value. But given the factors and the variables that we had in the data set, this is what we were able to work with. As we went to go ahead and analyze the diagnosis, this is what we were able to look at for the plots of the summary models. First, kind of most notably looking at the non-normality in the QQ Shapiro plot, we saw that there was a heavy right skew and was a presence of heavy outliers when looking at these plots. When thinking about this, we wanted to also take a look at the influential points, and we were able to plot this and then notice that a heavy amount of influential points by looking at the Cook distance as well as the plot below. Now, when we consider a solution for the influential points that were noticed in the plot above and the Cook's distance values, we decided to go with a robust regression, and this model was shown below. By running it through R, this is a summary that we were able to achieve, and we can see that this robust model had an improved impact, or an improved model, as we saw a reduction in the RSE. What was once in the original model nearly 12,100 for the RSE was now 7,716 in this new robust regression. By running Bootstrap after, we were able to see that this wasn't necessarily something that we needed to do. We saw that all the critical values ended up becoming equal, and Bootstrap just wasn't necessarily something that we had to do for this after running the robust model. By running the k-fold cross-validation, we're able to come up with an RMSE value and R-squared value similar to that of the model that we had previously run. And really all this told us was that the k-fold cross-validation validated our model successfully. Now, what we were able to conclude by comparing our models, a reduced and full model, is that we're able to see that living in the Northeast and living in the Northwest, there's really not a significant difference. We can see this by the F statistic and the fact that it's lower than the p-value. So we were failing to reject the null hypothesis. Now, when we consider what this actually means by failing to reject the null hypothesis, we're concluding essentially that living in the Northeast region versus living in the Northwest region, there's not a significant impact on an individual with their individual insurance charges. And this kind of was maybe against what we were assuming it would be, assuming that one region would likely have a difference in charges, but that's not what we saw here.
Moving on to the question, if does smoking have an effect on insurance cost? So for our dataset characteristics, we have Y as our insurance charges, and then we have as our quantitative data the ID, and for categorical, we have smoker, yes if they smoke, no if they don't, and then we have our interaction between the ID and smoker variables. So in our preliminary analysis, we can see that we actually already have a pretty good R-squared value. But when we run our diagnostic plots for the models, we can see that there is a little bit of non-normality with the QQ plot, with there being a right skew, and also there is a bit of a presence of outliers. So then when we do the diagnostic for the outliers, by looking at this from the hat values and cook distance, we were able to see the presence of several influential points. So when we have the old model, we include these points, but then when we create our new one, we'll take these out for our analysis. So in the approved model, when we take out those influential points as seen before, we have an approved R-square value by a little bit. It goes from 0.61 to 0.62 by removing this. So then when we need to check for multicollinearity, so we decided to perform a ridge regression. So while looking at the VIF, you can see that the K value of 0.14 has the values that are closest to 1. So that is the value we decided to go with at first when running ridge. But as you can see, after running ridge with that value, our R-squared value actually decreases to 0.5. And from running other values, we eventually came to the conclusion that at K equals 0 yields the best results, showing that we don't have an issue multicollinearity, and that ridge regression is not needed here due to K equals 0 being the original model. In addition, did do bootstrap, but again, this shows that it is not necessary for this model. And then when we ran our k-fold cross-validation, we can observe that the RMSE value is very similar to the R-square value, showing that our model was successful and validates this. So in conclusion, with our F critical value being greater than our F statistic, this shows that our p-value is not significant and we fail to reject the null hypothesis. So we can conclude that there is no impact on if you smoke with your insurance costs, which was very surprising to us because we figured if you smoked, you would have a higher insurance and costs. So this made us question and want to dive further into this topic.
And to understand the previous study more, we came up with a new question that whether BMI would have the same impact on insurance charges if the person was a smoker or not. So we created another initial model for the same, which contains charges, BMI, smoker, and interaction of BMI and smokers as our variables, with charges being our Y. Running the preliminary analysis, we found out that the model again performed good with an R-square of 0.74. So the next step that we took was run diagnosis plots again. But from the plots, we can see that there is an issue which mainly is with non-normality, outliers again, and a little bit of collinearity. But outliers and non-normality was a big problem, so we decided to tackle the same first. The first step that we took is, as we can see from the plot, we transformed the model with natural log, we transformed the y with natural log, and then ran the model again. As we can see the new QQ plot on this slide, the normality issue has decreased significantly. As a result, we went further with the same model where y was transformed. Outliers are still issues, so the next step we had to take was tackle with outliers. Here we can see the summary of linear model with y being transformed. Our R square in this case is 0.47. Now, running the diagnostic plots for outliers and influential points, we see there are quite a few of them, especially with studentized residual values above 2 and with hat values greater than nearly 0.009 and Cook's distance as well. And considering that, we went to find out the points that were influential and further eliminated them from the second model. Here is the summary of our improved model where the outliers and influential points are removed, and we can see that it drastically improved the results. Our R square jumped from 0.47 to 0.66 in this model. So we decided to continue forward with the same. After that, we ran the k-fold cross-validation to verify whether our linear regression is accurate and powerful. And from the results of k-fold cross-validation, we observed that the RMSE is 0.4413 with the R square being 0.6692, which was quite close to the one that we got from our improved linear model, which gave us an RMSE of 0.4436. That verifies that that means the k-fold cross-validation successfully validated our model. After which, I created a reduced model and a full model to run a GLT test for a hypothesis. So our null hypothesis was that smoker has no impact with BMI. That means the interaction term of BMI and smoker is 0, while our alternative hypothesis was that the interaction terms of smoker and BMI had an impact on Y. So then we came out with our F test statistics to be 54.39. And since the F statistic value is greater than the F critical value, the p-value is significant, which means the null hypothesis does not bind. So we decide to move ahead with the alternate hypothesis. From that, we can conclude that BMI does not have the same impact on the insurance charges when a person is smoker compared to a non-smoker. Also, from the regression equations from the previous slides, we can notice that there is a positive interaction term, which means if a person is a smoker, he or she has to pay more insurance charges compared to someone who does not smoke. And that is our primary conclusion from the study.
When thinking about the all of the hypothesis conclusions here together, this is essentially what we were summing up previously. There's not a significant difference in living in the Northeast region versus living in the Northwest. There's not a significant difference on insurance costs for individuals who smoke versus not smoke. But when we consider BMI in that, then we do see a difference between individuals who smoke and don't smoke. Now, what do we draw as our results? I mean, overall, we're very surprised by the results. One would probably naturally assume that those living in different regions would have different either higher or lower costs or charges, especially when considering the Northeast, where cities like New York and Boston are located, and people would readily expect that their insurance costs would be higher. But that's not all what we saw. Additionally, a significant habit like smoking was expected to lead to expensive insurance charges, but that's not necessarily what we saw. Now, when we considered things like BMI, then we saw smoking actually play an impact. Ultimately, we faced a number of issues, the first of which being that the R-squared value in our first hypothesis was extremely low. After running that model, we saw an extremely low R-squared value. And we acknowledged that while we attempted methods to up this R-squared value, there's not much that we could do to improve that without adding in additional variables that were not present in our data set. There was also other problems with the data. For example, there's very few individuals who smoked. It was not a true 50-50 split between smokers and non-smokers in the data set. And that interaction would be important for us to look at in the future. Other issues like the amount of categorical factors, of which the data set was primarily, as well as the presence of a lower amount of data than we probably would have liked. The American population is around 330 million people, yet this was only a sample of 1,000 individuals. In the future, we would probably consider a different data set when going about this project, maybe something with a much larger sample size that had less categorical variables and could give us more quantitative data rather than qualitative data. Altogether, we were pretty happy with our conclusions and what we were able to come up with. So big thanks from us here at Group